Today I will just solve few problems which I explained in the last class regarding the maxima, minima and the saddle point identification of nonlinear programming problem. Now again we are concentrating on the one dimensional unconstrained nonlinear programming problem. Let me take few example on that. This is one of the example. The function has been given as x to the power 5 by 5 plus x to the power 4 by 4 minus 5 x cube by 3 plus 3 x square by 2. We need to find out the minimum, maximum and if there is any saddle point or not. Now, if the function is f x is given to you, now the process is that, now one thing you have to just see what is the pattern of the function. First of all, if you can find out what is the pattern of the function, that would be nice. Now, for finding out the pattern, we have to judge whether the function has, in which part of the interval function has the convexity and in which part of the interval function has the concavity. Now, once the function has been given as a convex function in certain interval, here there is no restriction on the decision variable. That is why this is unrestricted in sign. X can take any value from minus infinity to plus infinity. Now, if we just check in which interval function has the convexity, then we can declare that within that interval there must be certain minimum point. I explained you in the last class regarding this. And if the function has the concave part in the some other region, then function must be having the maximum value within that. And if the function is changing from convexity to concavity, that means the pattern of the function is just changing in certain point, then that must be the saddle point. Now, I am not going into the geometry of the function of this. Let us try to solve this function first. For doing that thing, the necessary condition suggests us we will find out the first order derivative of the function f dot x. Then we will equate to 0, then we will get the stationary points of this. If this is the, if we consider the first order derivative, then x to the power 4 plus x cube minus 5 plus 3, 5x square plus 3x. Now, if we equate to 0, let me just simplify this. If I take x common, then it will be x cube plus x square minus 5x plus 3. Now, for this minus 3 must be one of the root of this, that is why let me consider minus 3 as one of the root. Then x is equal to x plus 3 must be the factor of it. Then this is x square, x plus 3, x cube 3x square minus 2x, x plus 3 plus x plus 3. Then x into x plus 3 and we are getting x minus 1 because x square minus 2x plus 1, x minus 1 whole square. Now, if we equate f prime x equal to 0, then we must be getting there are 3 saddle points for this. One is 0, another one is minus 3 and another one is 1. Okay. Now, for checking the maximum and minimum of the function, we will go for the second order derivative of f x. Then it would be 4x cube plus 3x square minus 10x plus 3. Let us see what is happening in individual 3 stationary points. At x is equal to 0, we get that f prime x equal to 0 as well as the f double prime x is equal to, if I just substitute 0 everywhere, it is coming 3, that means this is greater than 0. That means x equal to 0 must be the minimum point. Alright. Now, let us go to the next. X is equal to, let me consider 1 first. Then we are getting f x, then this must be is equal to 0. Okay. If we consider f double prime x equal to 0, our sufficient condition suggests that we will go for third order derivative of x. Now, third order derivative is coming as 12x square plus 6x minus 10. At x equal to 1, this value is coming 12, 22, that must be positive, that is coming 8, that must be positive. Since we see that from the sufficient condition that third order derivative is positive, that is why we cannot go further. We have to declare that this must be a saddle point. All right. At x equal to 1, f(x) must be changing its pattern. Now, let us go for x is equal to minus 3. F double prime x is coming as, I calculated, this is coming as minus 48, that is negative. That means at x equal to minus 3, there is a maximum point. Now, if this is the information we are getting from the necessary and sufficient condition, what we can see from the function that minus 3, if I just take the interval from minus 3 to plus 3, we see at minus 3 there is a maximum point. That means the function must be concave. After that it is going to 0, that means we are reaching to the minimum point. That means around 0 the function must be convex, and after that the function is changing its pattern. If I just draw it, just we see that we will get this function. Now, what we see here, at minus 3 we are getting the maximum value, and at 1 it is changing the pattern, and 0 there is a minimum value for the function. Now, for looking this one in a better way, I have given another function for you, just to see the function. Around 0 the function is, around 1 the function is changing its pattern, from concavity it is changing to convexity. Now, this is the function altogether. Now, you see one thing you should notice here, that if we are finding out the minimum, maximum and saddle point from after looking at the function picture, we could see that function at 2 from 1.8 to the function is increasing further and further. Okay? There is no information about the restriction on x, that is why x can vary from minus infinity to plus infinity, but x is changing its pattern and the function is going up and up after 2. I do not know where it is going. If we draw, we can find it out. That is why, though we found that at point minus 3 function was having the maximum value, that was the pattern of the function, maximum value, but by looking at the picture we could see the functional value is maximum at 5, but you see we are not able to get it. Why? Because that is the drawback of this methodology. As I was mentioning, in classical optimization technique, we are going for we are calculating the differential coefficients, first order derivative, second order derivative, if these are all exist. But one thing is that at the end point of the function, we are not able to find out the limit value of the function, rather we are not able to find out the first order derivative of the function. That is why these points are not coming into the picture when we are calculating the maxima minima. That is why by looking at the picture of the function, we can say these are all the minimum, maximum, these are all the local, these are not at all the global optima for the given function. Now, we have to, since we have identified the problem in solving the classical optimization technique, we have to see the solution, how to get rid of this problem. Now, that is why the next level of calculations are coming, that is called the numerical optimization I was mentioning. Now, let us take another problem. Now, for this problem we are trying to sketch the function first, then we will go for the maxima minima of the function. This is the function for us, f(x) equal to 2x to the power 6 minus 6x to the power 4 plus 6x square plus 10. Now, if I just ask you, you just tell me how to sketch this function. One thing we can do that we will first find out the concavity part and the convexity part of this function. Now, for doing this thing, for finding out the convexity or concavity, you know, we have to find out the second order derivative of the function. Now, if the second order derivative, if it is positive, one thing is either convex or concave, and if a double prime x is negative, some other. What is that? As we know, if double prime x is positive, that means we are getting the convexity of the function, and if f double prime x is negative, we are getting the concavity of the function. That is why let us see what is the value for f double prime x. Okay. Now, the x is again it is not restricted, it can move from minus infinity to infinity. That is why just through Excel I was finding out few values for x and the corresponding f x and tried to find out the values for f double prime x. What we could see here, if we consider the values, just you see from minus 1.2, minus 1.1, minus 1, minus 0.9, if it is moving further at 0, the value is 0, and after that it is going to minus, then it is going to plus. Okay. Where it is going, the changing its pattern, just look at the Excel file, you could see that it is changing its pattern at 1, because before 1 this is negative, after 1 this is positive. At 0 this is the minimum value, and at minus 3 we are getting the maximum value. Minus 3 is included here, yeah, minus 3 is not included here, that is why it is not there. Okay. Now, we try to draw the picture of it, and we could find out this is the picture of f double prime x. What we could see in the f double prime x, that after minus 1 the function value is, the double prime x is coming negative. After that 0 it is positive, okay, and at 0 we will see this is not a function f x, this is a f double prime x, alright. That is why function must be having the concave pattern, convex pattern here, f double prime x is negative, that is why. After that again we are getting the negative value, and after 1 it is changing from negative to positive. Okay. It is not maintaining before 1 and after 1, the pattern is not being maintained, from convexity to concavity it is going. That is why I just draw the function after that. Just to see, we are getting the concave part at minus 3, and at 0 we are getting the convex part of the function. Again at 1 it is changing its pattern from from the concavity to convexity. Okay. That is the thing. Now we are applying the classical optimization technique for maxima and minima. Now, if we just look at the function, we could see the minima is coming at 0 and maxima is coming at minus 1, and after that we are having the changing pattern at 1. That is why the first order derivative we could see now, oh no, at minus 1 also just we could see that it is changing its pattern. The stationary points are 0 plus minus 1. Okay. Now, f double prime x is this, and we could see at x equal to 0 f double prime x is positive, that is why it is having the minimum value, alright. And at x plus minus 1 f double prime x is coming 0, but f triple prime x is not 0, that is not double prime, that is triple prime x is not equal to 0. That is why we can say that since the n is here odd, that is why that must be the point of inflections at point plus 1 and minus 1. From the picture also we can see the same thing, same pattern. That is why you see, if the function is given by judging the convexity, concavity part, minimum, maximum part, we can find out we can sketch the function, rough sketch we can have. of the function, alright. But the exact, for getting the exact picture of the function, we need to study something more than that, that is the asymptote and all other properties we need to find out, then only we can sketch the function better. Otherwise, a rough sketch we will get through this only. Now, this is another problem, just see. Now, a farmer has statistical records showing that if 25 orange trees are planted, each tree would yield 500 oranges. But there is one information that if we plant only one tree extra, then 10 oranges per tree will reduce. Now, the question is given to you, how many trees should be planted for maximum total yield? For normal case, we are getting 500 oranges from a tree. Okay? Now, but if the next information, if we plant one tree extra, from each tree 10 oranges will be reduced. That means, we will get 500 minus 10 from each plant. Now, the question is that how many trees should be planted so that maximum yield will come. Now, let us to construct this problem, we have to just construct a function for solving this. Now, let me solve it manually. Let me consider the variable x as number of trees the farmer is planting in xx to 25. In excess of 25. Because initially the information has been given that in the normal case he is planting 25 plants. That is why in excess we are considering x plants are being planted. If x is equal to 1, then how much yield he will get? He will get 500 minus 10 into 25, because there are 25 plants. Okay? Now, if there are x number of plants, 490 into 26, because 25 plus 1 26, you are right. Now, if there are x number of plants, then what should be the number of plants altogether? It would be 25 plus x, total number of plants. Okay. Now, how much yield I will get? If it is normal, we will get 500 into 25 plus x, but this is not normal, there are x number of trees, that is why I will get 500 into 500 minus 10x, okay, and total yield would be this into 25 plus x. Now, I have to maximize this is my question, because I have to maximize the total number of yield, alright. Now, if this is the problem for us, then just look at the function. This function is coming as 125,000 plus 500 minus 500x minus 250x, it is coming 250x minus 10x square. Alright, we have to maximize this function. Now, let us apply the classical optimization technique. What we are getting? F prime x is equal to 250 minus 20x. That is why the stationary points are, if I just equate to 0, f prime x equal to 0 gives me that x must be is equal to 25 by 2, that is 12.5. Okay. Let us find out f double prime x for this. Double prime x would be minus 20. That means always it is negative. That is why it is suggested that you plant 12.5 number of trees for getting maximum yield. But you see, the problem is such a problem here. Certainly there is a restriction on the decision variable x, that always x has to be positive, it cannot be negative, number of trees cannot be negative. What else you are getting the restriction? Number of tree cannot be discrete. That is why this kind of optimization problem is being named as the discrete optimization problem. But if we see, if we just find out the feasible space here, we are considering the whole range from x equal to 0 to infinity, which is totally continuous, but that should not be. Always we will have the value for x as 1, 2, 3, 4, 5, etc. Okay, integer numbers. Now we are getting x equal to 12.5. That is why this process is not correct process to judge that we are getting the result, nice result for it. That is why that is the disadvantage of using the classical optimization technique. Now that is why there is another series of techniques are available, that is called the numerical optimization technique. There is a range of variations of the methodologies. Now today I will just discuss one simple methodology for solving the through the numerical optimization, and the advantage is that even the space is discrete, we can use those methodology and nicely we can get the solution of it. The very well known method you must have been learned it, that is the interval halving process. Now befoore to that, just I gave certain values, I was calculating certain values of f(x) and I just draw the picture of it, and certainly we are getting that at x equal to 12.5 we are getting the optimal solution. Here if we see, we are getting the points 0, 1, 2, 3, 4, 5 like that, up to 21 we could calculate. Now one thing is that, one thing we can say that within the range of 0 to 21 function is unimodal. That is why whenever we are getting a function, it is a better practice for us to just judge the property of the function. Let us draw it. Okay, draw the, if I am having the tool, if I am having any software for plotting the graph, do it, otherwise just use Excel as I did here. Just simple Excel will be sufficient for you. Put the value of x, calculate the value of f(x) and draw it. Okay, that is why classical optimization suggested 12.5, it is very much correct. Now this is not accepted, that is why we are going to the next level of technique, optimization technique, through which we will solve the problem. This is a very well known methodology, all of you must have been done in numerical analysis, interval halving process. There is another name to it, that is called the bisection method. We will solve the same problem and we will see how nicely we will get the solution for the same problem, where the solution will be, we can consider as integer. Alright. Now let me tell you the steps of interval halving method first. Now the first step, it is saying that whenever interval halving method tells you that, as we could see from the function pattern, that always the maximum is there from 0 to 21. That is why it is suggested that, let me consider 20, it is suggested that always from 0 to 20 you make the interval half of it. That is why we will get one part 0 to 10 and another part 10 to 20. After that, each part you make, you halve it. That is why we will get 0 to 5, 5 to 10, 10 to 15, 10 to 20. That is why initially what you do, you take the left point of the interval and the right point of the interval, and in between, in equally you space 3 points, so that whole interval can be divided into 4 parts. The process tells you that if A is the lower bound of the interval, this interval is called the interval of uncertainty, because we do not know, that is totally uncertain to us where the optima lie. Only thing we have some information function is unimodal. in between 0 to 20. Okay, that is given information to us. That is why 0 is A and 20 is B, we will have it and just name it with x0. After that, we will again we will consider the interval points x1 and x2 in such a way that x1 will be in between 0 to A to x0 and x2 would be from x0 to B. That is why if I just draw the interval, that interval will be A, B, x0, x1, x2. Now, we could see here that we are getting the point x0, that is the middle point of AB, x1 is the middle point of A and x0 and x2 is the middle point of x0 to B. Just look at the methodology we have written here. If f2 is greater than f0 and greater than f1 and we are looking for the minimization, minimum value of the function, certainly we are sure function is unimodal. That is why there is only one mode, there is only one minimum within the interval. That is a minimum cannot lie from within this region from x2 to B, because function is gradually increasing. Okay? That is why we will discard a part of the interval. Which part we will discard? We will discard the part from x0 to B and we will get the new interval of uncertainty as A to x0. Alright. Let us consider the other case, that f2 is lesser than f0 and lesser than f1. That means in the left side function is increasing and then in the right side function is decreasing. But if I just minimize the function, certainly in the left side, if in the left side function minimum cannot lie, alright. That is why we will discard that part. That is why you see we have written the methodology delete A to x0 and you consider new interval of uncertainty as x0 to B. Okay. Now, the other case, if we see that f2 is greater than f0 and f0 is less than f1, that means we are getting the around f0 we are having the minimum and the f1 one side is having the higher value, f2 one side higher value. That means the minimum cannot lie below to x1 and the beyond to x2. That is why we will take the new interval of uncertainty as x1 to x2. After that, what we will do? Once we will get the new interval of uncertainty, that one we will consider at the initial interval of uncertainty, we repeat the process. We will again find out 4 parts of the interval, we will find out new x0, new x1, new x2, we will repeat the process again and again. And how long we will do? We will repeat the process as long as the interval of uncertainty is very small. Okay? Or we have certain target that we want to get the accuracy of 10%, accuracy of 5%, then we can have the better this process can give us that kind of accuracy. Okay, in that way we will get the solution. Now, this is one of the method of numerical optimization. Whatever numerical optimization method you will get, you will see everywhere the challenge lies how to select x0, x1 and x2, because these are only the guiding points for selecting the minimum value of the function. That is why from the next class I will give you few more nice methodologies, and after learning all the methodologies together we will just compare all the methodologies. Okay? That is all for today. Thank you.